All right, so this is labeled Unit 6, and I've kind of we'll pick and choose some of these things, but here we're going to talk about roots, and we're most familiar with square roots. So the nth root, because it could be any number there, is written in this radical expression. This number that's labeled, this letter that's labeled n, this would be the index. And oftentimes we don't see anything there. So if you do not see an index, then it's assumed that it is a 2. I guess there should be an is in there. That it is a 2. In other words, that it is a square root. So if we don't see an index, we just assume it's second, that we do square root. The number under the symbol is called the radicand. And the symbol, that square root sign, is called the radical. And so there are radicals that can have more than one root, like a positive or a negative. Like to get 81, it could be positive 81 or it could be negative 81. But when we're doing this, we typically are just indicating the positive one, right? So we're going to go back to these often. So we're going to list the first 12 perfect squares. If you ever needed to do that and you weren't sure, just it's all your doubles in multiplication. So 1 times 1, 2 times 2 is 4, 3 times 3 makes 9, 4 times 4 is 16, 5 times 5 is 25, 6 squared, 36, 7 squared, 8 squared, 9 squared, 10, 11, and 12. And then we have seen these because when we did difference of squares, when we were factoring, those were numbers we kind of looked for difference of squares. And so we have some next. These are all perfect square roots. And if it's not in this list, or it's not one we know off the top, then we can use our calculator. And it is at, I think it says second. Is it second? And some of them say shift. Second, and then press x squared. And then you're going to see the symbol. And then you could put in, for example, 484, and then hit equal 22. So sometimes we might just know, like, well, 20 times 20 would be 400. So it has to be more, and to end in a 4, so we might be able to guess and check, but the calculator will make that easy for us. So this is 22, yes. And then square root of 81 is, of course, 9. And square root of 64 is 8. So this part, you're like, wow, you're not kidding. This is like lots easier. It gets a little harder, but it's still not too bad. So we have a few more perfect squares here. But you see some things start happening here with number 4. Yeah, if there is something on the outside, we're going to simplify the radical, and then we multiply it times what's on the outside. So the square root of 4 is 2. So then this just means 18 times 2, which is 36. Okay, and you wouldn't necessarily have to write 18 times 2 first, but so you know where that number comes from. So then square root of 256, 16, I believe, and then 3 times 16 is 48. So for number 6, negative 5, and then square root of 121, so 11. So then this is negative 55. The fractions, everybody gets all worked up about fractions. Just think of the numerator and denominator separately. and then leave your answer in a fraction form. Yes, exactly. So 1 over 4. And 3 over 10. Because the rules for radicals, this is the same when it's one large radical sign as if it said radical 9 or square root of 9 over square root of 100. And then same here then would be 5 over 7. Then comes the trickier part, and really what we did when we were using difference of squares, but we had to do GCF first, is kind of what's going to happen here. There's nothing to find a GCF for, but we're going to break down the perfect square into a product that one of the factors is a perfect square. We're going to break down the non-perfect square, the radicand. So 24, I want to think about that list of perfect squares. So is 8 a perfect square?
No.
Oh, so don't use 8. 4, right? We're going to have to use 4. So 24 is the same as if I do 4 times 6. The 4 is a perfect square. So the square root of 4 is 2. And then the guy who's not a perfect square, that's left under the radical. So we're pulling out the square root of any perfect square factors. You want to take the biggest number you can. That's the other trick. We don't want any perfect squares left under the radicand. So when I look at 48, let's say if I just thought 4, 4 goes into 48, but then I'd have the 4 and a 12, and 4 goes into 12 again. So I got to go bigger. So what's my perfect square? The biggest perfect square that goes into 48? 16, yes. So 48 could be rewritten, and you could write it this way, under 1 or under 2. Exactly. And so then this is 4 and square root of 3. Now, let's say that I did this, and instead I went 4 and 12. But then I should look at 12 and go, uh-oh, 4 still goes in there. And then this would be like 4 and 3. That 4 would send a 2 to the outside. And then 2 times 2 would still be 4. I mean, it's kind of like reducing a fraction. You can still get there. You might just take longer steps. So you really want to think of the largest one that would go in there. So what about 72? 36. Yeah, 9 works, but it's not the biggest. So when you look at that list, a lot of times I just tell students to keep that list handy. And then, so 72, well, the next smallest is 64. Well, obviously 64 is not going to work. 49, no. And then 36, I mean, I can even grab a calculator. 72 divided by 36, oh, yeah, it works. So I kind of start big and work my way down, kind of running through the possibilities. Sometimes some of them will be kind of obvious, sometimes not. Again, if we use 9 instead of 36, then we should still see, 8. 4 goes into 8. And then we would do the process I had over here and keep going. So if we use 36, that's going to be the most efficient way because that's the largest perfect square that goes in there. And then 6 radical 2. So, and typically that's the way we would read that, 6 radical 2 or 6 square roots of 2. We could say either of those things. So 63, 9, yes. And then if I don't know off the top, then I do. 63 divided by 9, I get 7. So this is 9 and 7, 3. So I actually take the square root of the perfect square, and then the one that doesn't have any square factors left is stuck inside. 90. 9 again, yes. So 90 is the same as 9 times 10. The 9, or hello, not 9 times 90. 9 times 10. 9 sends a 3 to the outside, but there is no other square factors in 10, so just square root of 10. $175. You tell me, does 81 go evenly into 175? No. Got an ideal one? 25, yeah, 25. When you see something that, like, if you put a decimal in it, it looks like something you could make out of quarters. 25. So 175, 25, and so then might have to do a little math. That's 7 times. So this is 25 times 7, which would be 5 radical 7 then. So we could also have square roots with variables. Now this, and even the way it's written in the words here, sounds a little worse than it is. Typically I just think of it as we're going to divide by 2, and any remainders are for the exponents. We're going to divide by 2, and any remainder is left under the radical. And you'll see what I mean here real quick. You'll pick up on this. This is actually probably easier than the number. It's easier to do the variables than the numbers. So if that is an m, that m being the exponent, if it's a multiple of 2, then I'm just doing a to the m divided by 2. So if it's second power, it becomes first power. So this is just x. If it's sixth power, that becomes m to the third. Now keep in mind, as always, our exponents and our coefficients don't behave the same way. This is still the square root of 9, which is 3, and then divide the exponent by 2, which is just 1. So if it's just a 1 for the exponent, I don't have to write that. Square root of 64, 8, and then half of 4 makes that 2. And if there's multiple variables, we just do the same thing for both. So the square root of 100, 10, divide the exponent by 2 on the x, divide the exponent by 2 on the y. Square root of 49, 7, and then each exponent gets divided by 2. And if you would like, I mean, you can write a to the first. It's not necessary, but it's not incorrect to include that 1 as the first power. So when they're even, pretty simple, pretty straightforward. And if they are odd, like you divide by 2, it doesn't come out even, it just means someone's going to be left underneath. The remainder, and since we're only dividing by 2, the remainders always just would be 1, or just the variable. So y to the 5th, when I divide 5 by 2, I get second, and then the 1 extra guy is still trapped under the radical. So just like how if we had extra numbers that didn't have perfect squares, they were left under, now we have a variable under. It can be that some variables come out completely and some don't. So like here for the a, we're going to send an a to the outside. 2 divided by 2 is 1. A b to the outside, but the b has a leftover, so there's still 1b left under. So here I would have 2 divided by 2 is 1, so x to the first on the outside. 3 divided by 2 is also 1, but he's got 1 left under, and then z divided by 2 is 2. Now, you could write that radical for the odd at the very end. Oftentimes, I just kind of leave some space and go ahead and write it as I move across. So, 144, so 12. k, and then still 1 under. So 9 r to the third, s to the second, and then we still have r. So if you're worried you're going to forget the ones that go under, just leave yourself enough room for like the s's. Go ahead and put that r under while you're thinking about the r's. So square root of 196, 14, c to the second, and then I might do this. Just move over a little bit, put my extra c under, and then just simply d. And then as you might be able to predict, what's going to happen next is we might have both numbers that aren't perfect squares and have some variables that aren't second power. And you will find that you have varying degrees of comfort of what you can do mentally and what you need to write out. I think with the exponents, it's very easy to do it without rewriting a lot of things, but sometimes the numbers, we may still need to do that. So I might just write 4 times 2 and then my x to the 6th. So the 4 is going to send a 2 to the outside, x to the 6th, 3, but then there's also going to be a 2 here. And the radical and whatever is in it is going to go at the very end. So we don't want 2 radical 2 and then x to the third. For one, it can be misinterpreted, like it could be easy to think that the x to the third was under the radical. So everything that's left in the radical, even if it's coefficient, it's going to be at the end. So 50, so 25 and 2, so 5, and then the x can come out with the 5, and only the 2 is left under. If there are numbers and variables, they can absolutely share the same radical as they were at the beginning anyway. So 68, even though it still seems pretty big, 4 is like 4 and 17, that's as best we get. Because 17 doesn't have any other factors, so then 2 to the outside, a p to the outside, and then 17 and the extra p underneath. So I've got 9 times 5, and then my n to the 11th. And some people will write this, n to the 10th, and then n for the extra guy. That's kind of the leftover guy. I just usually know if it's an odd number, I'm going to have one left. But if that helps that make more sense to you. So this would be 5th, and that's from this part and that part. And then the 5 and the extra power of n are still left under the radical. So 27 would be 9 and 3. And remember that that 16 is only on the y. So the 9, square root of 9 would be 3. There's still an extra 3 under. The x is trapped under because he doesn't have at least a power of 2. Y is outside. 16 divided by 2 is 8. So there are a few little steps going on in your mind there, but there's not, I mean, I guess if you want to write yourself a note, but the variable part especially tends to be something people pick up on fairly quickly. So 180. Is 18 a perfect square? So 180, 100 definitely doesn't go into it, right? Let's work our way down. 81. 81. Does 81 go evenly into 180? No. 64? No. How about 49? No, not ending in that 0. How about 36? 180 divided by 36. It goes. It does. So sometimes you just need to try that. Or the other thing, if you think about, if at first you think 9 times 20, but then 20 still has a 4 in it, right? So if you first thought 36, 36 does work, but I'm just saying if that's not obvious to you, and you think of 9 times 20, the 20 is still a perfect square, right? It's 4 times 5. Let's put the 9 and the 4 together. That's 36 times 5. Or try big and work your way down. So 36 times 5. And then, of course, we've still got our variables. So the 36 sends a 6 to the outside for that square root. I'll go ahead and make this over here. 5 is going to be left under. Then I'm going to look at my x's. 3 divided by 2 is 1 with 1 extra left under. Y to the 8th. 8 divided by 2 is y to the 4th power. No y's left under. So when there starts being multiple variables, the multiple variables I don't think really makes things more difficult. It's when the numbers start to get bigger and we're trying to be sure that we choose the largest perfect square that I think things are trickier, so to speak. So 160. 16. So 16 times 10. And then I've still got my a to the... And if you'll remember and you won't forget about your variables, you don't necessarily have to rewrite that part. But I would just also caution you, I wouldn't want anyone to just give the answer as that and then forget that there were variables at all. So then we have 3 divided by 2 is 1 with 1 left over. 6 divided by 2, b to the 3rd. B was an even power, so there's no b's left under the radical. How about 108? 9. Anything bigger? This would be 9 times 12. Does 12 have a perfect square in it?
4 times 3,
Yeah, so since 9 times 12, so 12 is a 4, has a 4 in it. So let's rearrange that and do the 9 and the 4 times each other, which would be 36 times 3. Now, again, if you stuck with 9 times 12, you just need to do another step because you should not have a number under that still has a perfect square in it. And then, of course, we still need to think about these. So I've got 6, r to the 9th, just dividing those exponents by 2, s, 13 divided by 2, 6. I've still got the 3 under, no r's, 1s. So you could write your whole radical at the end or leave yourself some space and put it in there as you go. And like I did here, in this case, I did not rewrite my exponents and my variables, but I need to be sure that I don't forget about that part of the problem if I don't rewrite it. And sometimes you might find that you're like, I can kind of do this in my head. 72, I think Muhammad told us earlier, that's 36 times 2. So that would send a 6 to the outside. There would still be a 2 under. And then half of 9, 4 with 1 extra. Half of 12, 6, no extra. Half of 2, p, just first power, no extra. So all the ones with even powers, kind of at a quick glance, as I kind of check myself, if the variable had an odd power, there should be one of those variables under. And because we're doing square root, we're always dividing the exponents by 2, then you don't ever need an exponent underneath. 63, I think we saw that one earlier, 9 times 7. So 3, 7 under. No z's underneath since z was an even power. So 252, we're getting on the bigger side. 36 goes into 252? How many times? 36 times 7. Did you just do some experimenting with that?
Yeah. Just divided on.
Yeah, just start,
64, 36.
Right. Like there's only certain things that would even make sense, right? You're not going to try 25 because it doesn't end in a 5 or a 0. So 36 and 7, so 6 to the outside, 7 left under. The x is only going to be on the inside, it doesn't get to come outside. The y, only on the outside. The z, and z. So notice even though the x is under, like the coefficient is the coefficient for everybody. So it's not like you write it in 2 separate parts. Everything that's on the outside is all going to be smashed together. Everything that's left on the inside is all under 1 radical. How about 392? Maybe 64? Nope. Maybe not. Ooh, maybe 49.
Yep. Got an 8.
Oh, so we need to even go bigger than 49. Okay, so now here's what I do, because I don't want to just be trying random stuff, right? So if I know that it's 49 times 8, break down 8 to 4 and 2, then put the 49 and the 4 together, so 196, which is actually 14. I mean, when you take the square root. So 196 times 2 is 392. So I just kind of rearranged the factors. So then we would have 14 on the outside. A 2 is going to be under. A to the first on the outside. B to the first on the outside. C to the first on the outside. And a C under. Also, if you see a fairly big number that you don't recognize, it's always worth a try to see if maybe it is a perfect square. If just maybe it's a perfect square, so that you don't end up trying to break it down to find out like, oh, I could have. But obviously if you use square root and it's a decimal, then you know you've got to break it down. So you have Homework, there's some spots that's scratched off because we only talk about square roots, not cube roots. So there are, I guess, about 12 problems. More than that, I feel like. 18 problems on page 4. And then there are 20 problems on page 5. The ones on page 5 are like what we just did. All right, so I'll give you guys some time to work on that, and then we're going to talk about quadratic formula.